In this video, we'll talk about Rolle's theorem, which is a neat result in this class, as well as an application to how it can be used. So Rolle's theorem, the proof of which we'll deal with in a future video, is a nice result, and we'll draw some pictures of how it comes together. So what does Rolle's theorem say? Well, Rolle's theorem says that if I have a function f, and this function is continuous on some closed interval, if it's differentiable on the open interval between them, and the values at a and b are the same, then there must be some point between a and b where the derivative of f is 0. It doesn't say there's not more than one, but there is at least one point c between a and b where this derivative is 0. This is a picture of what this might look like. If my function hits both of these points, and I'm going like this, well, if I'm going to get back to b, I have to turn around at some point. And wherever I turn around, that point gives me a horizontal tangent, which has derivative of 0. That's the basic idea of the proof, but you can think of it this way as well. The sort of point is, if I start at a at 0 and end at b at 0, I have to turn around somewhere in the middle. And that turnaround point is a horizontal tangent, is a point where the derivative is 0. We'll see the proof in a future video. Now, what's one way this theorem can be used? Well, the main application of Rolle's theorem directly is something like this. I want to show this function here, x cubed over 6 plus x squared over 2 plus x plus 1, has exactly one real root. This is sort of a strange application of this because it is sort of a, we would call it math of proof by contradiction. But the idea being, if I had two real roots, then I'd have a problem. So let's start this in one direction. How do I know that this function has a real root? The answer is yes. And how do we check that? Well, we can check that with the intermediate value theorem. If I look at, say, f of negative 1,000, that's going to be really negative. Why? Because it's going to give me a negative 1,000 cubed plus a positive 1,000 squared. That's not going to make up the difference. So because that x cubed term is there, this is going to be a negative number. So that's going to be negative. And f of, say, 1,000 is going to be positive. Since this function is a polynomial, it's continuous, and therefore intermediate value theorem applies, giving me that it has a root between these two numbers. Now, what about having exactly one root? Well, to do this, we're going to assume that it has two. So assume that a and b are two roots of f of x. So there are two numbers where f of x equals 0. So f of a equals 0 and f of b equals 0. So by Rolle's theorem, it's a polynomial, so it's continuous, it's differentiable everywhere. So by Rolle's theorem, there is a c between a and b, so that f prime of c equals 0. Good. What's f prime? Well, f prime for this function is now x squared over 2 plus x plus 1, just by taking a derivative. If I factor out a 1/2, I get 1/2 x squared plus 2x plus 2, which if we look at this some more, this is 1/2 x squared plus 2x plus 1 plus 1. So it's 1/2 x plus 1 quantity squared plus 1. Think about this graphically, this is a parabola that would just touch the x at -1, but now I've shifted it up by 1. This function never crosses the x-axis. What does that mean? This means the equation f prime of c equals 0 has no solutions. But Rolle's theorem guaranteed me a point c where this happened. That's a problem. That gives me a contradiction because I said this point must exist, and then I said this point can't exist. That's a contradiction. Therefore, I did something wrong, and the thing I did wrong was assuming that I had two different roots. There cannot be two different roots of this function. There cannot be 2 points where f of x equals 0. We know there has to be one, and there can't be two. Therefore, there must be exactly one. So therefore, f of x has exactly one. That it has to have at least one by IVT, it can't have 2 by Rolle's theorem. Therefore, this is exactly one root, which is what I wanted to show for this problem. That's a statement of Rolle's theorem, as well as one which can be applied to give you certain information about functions that you might not be able to obtain otherwise.